Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at norms in other vector spaces. So up until now, we've been looking at norms in finite dimensional vector spaces. We will now look at the 2 norm for discrete and continuous signals, as well as the infinity norm. We will look at a few examples. Now, given the discrete signal x, we could define the 2 norm of x to be the square root of the infinite sum of the squares of the absolute values of the entries of x. This definition works whether or not x is a complex or real discrete signal. We, however, do have a problem. Under this definition, some discrete signals have a norm equal to infinity. So that is generally unacceptable. For example, the discrete signal that is all ones. So the discrete signal where the 0th entry is 1, then 1, 1, 1, 1, and so on. Why is that infinity? Because the absolute value squared of each entry is 1, and the sum of 1 an infinite number of times is infinity. So we cannot have a vector that has an infinite norm. However, the subset of all discrete signals that have finite norms, that is, all discrete signals such that the square root of this infinite sum is less than infinity, that actually forms a subspace of the vector space of all discrete signals. Alright, so that's useful. That means if we have 2 signals that have finite norm and we add them together, then the result will still be have finite norm. And of course, it should be more obvious that if we multiply a discrete signal that has a finite 2 norm, that of course alpha times that signal is simply going to be alpha times the original norm, absolute value of alpha times the original norm, and therefore it too will have a finite 2 norm. For example, if the absolute value of gamma is less than 1, then the discrete signal gamma to the n is such a signal. For if we were to square every entry in this, square the absolute value of each entry of this signal, we would be calculating the square root of the sum of the absolute value of gamma to the k all squared. However, that is equal to, by the properties of arithmetic, the square root of the sum of the gamma squares in absolute values raised to the power k. Well, that is just a geometric series where the ratio is the absolute value of gamma squared, and therefore that infinite series is 1 over 1 minus the absolute value of gamma all squared. So for example, the discrete signal, which is the geometric series or sequence with ratio 1/3, has a finite 2 norm as described on the previous page, and its 2 norm is equal to the square root of 1 over 1 minus the ratio squared, which in this case is 1 over 9. This calculates to 3 over 2 root 2. Now, if we were to divide every entry by 3 over 2 root 2, this would give us the following discrete signal, which would therefore be a unit discrete signal. Notice that this one is a a geometric series, but now one that starts with 1/3, 1/9, 1 over 27, and so on. And it is each term in that is multiplied by 2 root 2. Now, given the discrete signal x, we could define the infinity norm to be the maximum possible value or absolute value of any entry. However, we can't really use maximum because the maximum may never actually be achieved. So instead we use the term supremum, but you can sort of think of it as being a maximum. The subspace of all discrete signals for which this norm is finite equals a subspace we've already seen, the subspace of all bounded discrete signals. Now, given the continuous signal defined on the half-infinite interval from 0 to infinity, we can define the 2 norm on this not using a sum, but rather using an integral. So the 2 norm of this f would be the square root of the integral of the absolute value of f of t squared integrated from 0 to infinity. Now, once again, a lot of functions have an infinite square integral. For example, the function 1. If we restrict ourselves to those functions for which the 2 norm, as defined here, is less than infinity, this also forms a subspace of all continuous signals. This is actually called the subspace of all square integrable functions. And this has applications in various areas of engineering, including controls. So, for example, here we have a function f that is defined to be e to the negative t times sine of 10t. So this is a decaying sinusoid. In your calculus course, you will learn how to calculate this particular integral, and you will find that it equals 1/5. Therefore, if we were to divide the above function by 1/5, that would give us a unit function that is one that has a square integral from 0 to infinity of 1. So, following this topic, you are now aware that there are norms that can be defined on discrete and continuous signals. And you understand that these norms are also analogous to the finite dimensional norms. You will not be using these too much in this course, but later on in your engineering career, especially in some of your other courses, you will be looking at such signals and you will need to calculate such norms, especially if you're trying to calculate the distance between two such signals. Here's the references, the acknowledgements, colophon, and a disclaimer. Cheers!